Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Dave Ansell. First of all, have you got any strange science stories or anything that rocks your boat?
So a bit of a blast from the past. Do you remember airships or
yes.
sort of Zeppelin type things?
Yeah.
Great big sort of flying things being held up by helium, which floats in air, so you hold them up. Well, they might be coming back. The American government has ordered, actually a British company based in Cardington, to build them some sort of big 300-foot long airships.
Wow.
They're not quite conventional airships, because the problem with the conventional airship is they're called light than air aircraft, but actually they have to be exactly the same density as air, because if they're too light, they float and carry on going upwards until they pop.
Yep.
If they're too heavy, they fall down and crash. So they've got to spend the whole time, either if they're too heavy, they've got to drop some ballast, or if they get too light, they have to vent off some helium, when helium's expensive. So it's a big problem. But there's a British company which has come up with a solution for that. The airship they've got is called the Sky Cat. They had a little toy one called the Sky Kitten, which they've been playing with. It's rather cute. But the idea is a catamaran. So you have two airships, you glue them together, and then you have a sort of a membrane between the two.
Right.
And so it basically looks like a very short wing. And so it can get some of its lift by going through the air like a normal aeroplane, but most of it from the helium. Which means that it can always be slightly heavier than air, so it doesn't blow away if you land.
Sure.
And you don't have this problem with having to keep adjusting your density all the time. And so the Americans want one to fly around, sort of an unmanned one, which fly around places like Afghanistan and look down on the ground so they know what's going on. And they reckon it should be able to stay up there for sort of 20 days, carrying about a ton of payload.
Gosh.
And so maybe at some point we'll see airships flying around again.
But isn't that going to be better for the carbon footprint of planes?
They are supposed to be, not necessarily for this particular thing, but they do also have plans for building huge ones which would carry sort of 1,000 tonnes. And that would be slightly better than planes, a bit slower, but definitely use sort of a quarter or a third of the energy of a plane to move a ton of stuff from here to there. So maybe we'll be seeing more of them.
Wow, that's quite something. Always so scary there, because all the films that you see, there was never a happy ending with them, was there?
Oh, they were all hydrogen filled, and they also had a tendency to make the covers of them out of very, very flammable materials.
Yeah.
Because they used to use a thing called dope, which is basically nitrocellulose with an explosive, so it was all a bit flammable.
Yeah.
But the modern ones are made out of much less flammable fabrics, because fabrics got a lot better, and you fill them with helium, which doesn't burn, doesn't react with anything.
Let's start then with that question from Claire, who says, apart from the heat and the force needed to get planes up through our atmosphere, are there any other reasons why usual aircraft couldn't cope in our solar system?
Well, the biggest problem is that the way a normal aircraft works, where it moves, where it flies, and how it stays up, is by basically taking air at the front, whether it's with a propeller or with a jet engine, and then throwing it out the back. And so the plane is throwing the air out the back, which means that it's pushing on the air backwards, so the plane gets pushed forwards. It's also the way the plane stays up, because the wings push air downwards, and if the plane is pushing air downwards, then the air pushes the plane upwards. It's a really fundamental property of the universe. Newton worked it out. Every action has an equal opposite reaction. Basically, if you push something, it pushes you back. So if the plane gets high enough out of the atmosphere, normal planes stop working over about 50,000 metres. There's not really enough air to be able to still work anymore. So there's just not enough air to take in and both push them along and hold them up. The planes have got higher than that, but they tend to be basically rocket-powered planes. You'd also have to have big problems with conventional plane, because the way that you get air to breathe, even if you go very high up, is by concentrating the air which is outside. They compress the air from the outside, and if you get high enough, there's not enough air to compress, and so you wouldn't have anything to breathe. And yeah, there's probably a few other problems, but the major one is there's just nothing to push on. There's no way for the plane to move. You need a rocket.
Now, Ralph in Stanford has said, with the weather changing from hot to cold in the space of days, why is it that when it rained on Tuesday evening there, although the temperature was not hot, we still had a thunderstorm? So why would that be?
Well, you tend to get that thunderstorms associated with lots and lots of energy, sort of very high energy sort of weather. And that tends to happen when you mix cold air and warm air, because the cold air will come in, push the warm air upwards. Basically, cold air is denser than the warm air, so the warm air will float upwards above the cold air. As it rises, it expands, cools down, all the water in it falls out. You get lots of very heavy rain. You get all sorts of strange electrostatic effects. Raindrops can rub on air and other raindrops. Things can charge up and you get lightning. So actually, you would probably expect thunder to be associated with a change from really warm, humid, muggy conditions to cool conditions. And also, just because it's cool where you're standing doesn't mean there's a lot of warm, muggy air above your head, because air masses can sit on top of each other. So, I mean, in fact, when it's going from warm to cold, that's when I'd expect you to get thunderstorms.
Gerald has come up with this. He says, I have been looking for longer speaker cables and have been stunned by the price. Asked for leads and cable in modern home theatre systems, 50p to £12 per metre. Ouch! Other than having well-made good connections and plugs that don't rust or corrode over time, what is the science behind pure copper, oxygen-free, silver wires, figure-of-eight windings, solid core and Teflon coating? Gerald, I totally agree. I have no idea, but perhaps Dave does. Dave?
I'm not really an audiophile, so I'm generally fairly suspicious of all these things. I think the argument for certain things like using silver or very, very pure copper is it reduces resistance slightly. But as a physicist, my immediate effect is, can't you just use a slightly larger wire? Then the resistance will be smaller, and it's probably far cheaper than using all these really exotic materials. And I mean, I guess if you have a low resistance, you get slightly less current noise, but that's going to be minute compared. You get sort of, you've got high resistance, you get current jumping across the resistance, and you get a little bit of noise, but it's going to be very, very small. I don't know. My general feeling, although please don't nobody sue me, my impression is that a lot of these things are just ways of extracting money out of people.
I have, they still work as well, some copper speaker leads for PA equipment, and I bought them because they looked pretty, because they were clear and you could see the copper inside, which is great because you could see if there was any breaks then, which was perfect sense, and that's why I brought them. And I think they must be 20 years old and they're still working.
I mean, it's normally the cables which break on things, because if you bend them all the time, then they can snap. And I can imagine you might have a better quality one which is less likely to snap, and actually a pure copper is going to be slightly more flexible. So you might get slightly less issues with them bending and snapping. But I'd be very surprised, especially if it's sitting still, if it's worth the money. But then again, I'm not an audiophile, so what do I know?
We're going to go to the phones now because Alan is on the line. Hi, Alan.
Hi there, Sue.
Hi, you're through to Dr. Dave. What's your question?
Hello, Dr. Dave.
Hello.
You might find this a bit of an unusual question, and you may think the question itself really gives the answer, but to me it doesn't. But the question is, what do we smell when we smell onions? And I suppose you could even say the same about garlic. What is it we're smelling? And how comes it can travel such great distances and yet you can still smell it?
The smell of onions is associated with a group of compounds called thiols. They're organic compounds, so they've got carbon, oxygen, hydrogen in them, and some sulphur in there. And they're quite nasty compounds, and when they get into your eye, I think they actually oxidise a bit, which is when they react with oxygen, they turn to something quite nasty, which your eye reacts to. It makes you cry. But it's these compounds which your nose is incredibly sensitive to them, and you can smell them from a long, long way away. And they don't really degrade that quickly, so I can imagine you could smell onions from quite a long way away.
Just because of the volume of it, does that then give it a greater distance?
Well, I mean, because a smell is basically molecules of a substance getting into your nose, and then they trigger some receptors inside your nose, and then that sends a signal to your brain. So the more of them are in somewhere to start with, as they spread away, they're going to get more and more dilute. So the more you started with, the further they're going to get at a concentration which you can still smell them.
And garlic is the same?
I imagine it's not quite the same compound, but they're quite strongly related, so I would have thought it's a similar one. I'm afraid my knowledge on it isn't entirely in depth, but they smell similar enough that I would have thought it was another thiol, if not quite the same one.
Right, all right, thanks very much.
You're welcome, Alan. Thank you. Bye. Let's go now to a question that was sent in by Dom in Newmarket, who says, how do they extract vegetable oil from vegetables? I've often wondered that. Olive oil, you see, they press and that. So
Yeah.
how do they do it with normal veggies?
I don't think vegetable oil is necessarily coming from the vegetables which you're thinking of. It's not coming from things like carrots or onions or any of these sort of things. I think it tends to come from, and a lot of it comes from oilseed rape,
Yep.
which is the thing with very, very bright yellow flowers, which you sometimes see whole fields full of. Other vegetable oils tend to come from seeds, so you get linseed oil
Yep.
and sunflower oil, so again coming from sunflower seeds. And I mean, if you've ever eaten a sunflower seed, if you kind of squash it, you do get a kind of oil coming out of it.
yeah.
It's quite an oily thing, and so I think they do just squash them. If they want to get more of the oil out, they'll heat them up first, because this makes the oils more runny, so it's easy to squash them out. I think with things like olive oil, the sort of first pressings are done cold, and then later they tend to heat them all up and get the last itsy bitsy bits of oil out of them, which apparently taste slightly different. But yeah, I think you start off with an oily vegetable or an oily seed, and then you squash it.
All right, well, let's go on to email now. This one has come in from Howard, who says, hi, Naked Scientist. Just want to say I love the show. I had a question which a professor asked us a few years ago. Is leaving a light on a waste of energy?
Yeah, I think the thing is, he was wondering, the professor had this argument to his wife. They had a big argument, apparently. And he was saying that in the winter, when you're having to heat your house, if he leaves the light on, then his heating isn't going to have to work as hard, so it's not going to waste any energy. And that actually sort of depends on how he's heating the house. If he's heating the house with electricity, then the heat coming from his light bulb is exactly the same as the heat coming from his electric heater in the corner. And therefore, if the light bulb is on and the electric heater isn't on for quite as long, then it really doesn't matter. The problem is that the heat coming from all the electricity, or the energy in electricity, whenever you make electricity, especially in a coal power station or something, you're wasting about half of the energy in the power station, because the fact that you lose it as hot water. If you've ever seen the big cooling towers with what looks like huge amounts of smoke coming out, it's actually steam. Because the way a steam engine works, which is what a big power station is you heat water, you get it very, very hot, it boils, you then run it through a load of turbines, you then have to cool it down at the other side, which sort of creates a vacuum and increases the pressure difference. And so you need to dump all that heat at the end, because there's still quite a lot of heat in the steam once it's gone through the turbine. And that tends to be about half of the energy in the fuel. So if you're heating with electricity, just with a straight heater in the corner, then you're wasting half the energy. If you're just burning gas, then all of the energy in that fuel is going to heat your house. So it's better to heat your house using gas than it is using electricity in a light bulb. So leaving the light on is actually wasting energy. So yeah, it depends. And if you're heating your house using some kind of more environmentally friendly means, like hot solar panels in the roof, or with some kind of heat pump, which you can pump up to sort of 7 or 8 times as much energy using 1 unit of energy, electrical energy, then it's much better to use your heating system and not the light bulb.
If you're enjoying Ask the Naked Scientist, then you might like to check out The Naked Scientist, our regular roundup of the world's best science. Each week we take a look at the latest science news, talk to top researchers working at the coalface of discovery, and also get our hands dirty with a science experiment that you can join in with too. So make it a date and prepare to strip down science on the web at nakedscientist.com/podcast. Right, let's go to the phones now, because on the telephone we have the one and only Tony. Hello, Tony.
Hello.
Hey, it's nice to hear from you.
Sue.
Oh, you're through to the one and only Dr. Dave. What's your question?
Right. Well, I'm old enough to remember the doodle bugs during the war.
Mm-hmm. Yeah.
And I can't remember how their engine worked, because it wasn't a propeller, obviously, and it wasn't, what do they call them?
A normal jet engine. Yeah, they had this very distinctive buzzing noise, sort of about 50 hertz, maybe 100 hertz, kind of horrible buzzing noise I've only seen them on films. They were actually quite an interesting design, as quite a lot of weapons are in a slightly depressing way. They were basically a tube, and on the front of the tube there was a valve. So there were basically lots of louvers, which would open and close, so a bit like a big valve. So if you just push the tube through the air, all the valves would open and let air into the tube. It would then squirt a load of fuel in and then ignite it with a spark plug or something similar. And then this caused a big explosion inside the tube, which would explode in both directions. But this would shut the valve, so all of that explosion would get shot out the back. And so all that hot gases would get shot out the back, which would push the Doodlebug along a bit. It would then, once the explosion had finished, the valve would open, more air would come in. You fill it with fuel again, ignite it, and it would go bang, and it would squirt all the hot gases out the back. So it was actually a form of jet engine. It's called a pulse jet.
Yeah, it was. It was the paraffin, wasn't it?
I'm not sure what the fuel was.
Yeah, I think it was paraffin.
I could imagine it was, because, they were very short of petrol at that point in Germany, so they'd be trying to make anything work on paraffin if they could.
Yeah.
But very ingenious and probably very, very cheap to make, because it was just a tube with a valve on the front.
Very scary.
It was no use for modern aircraft, little aircraft, for example, today.
They are horribly noisy, I think, is one of the
They're
problems.
very noisy, yeah.
The other problem is the valve didn't last very long. But on a Doodlebug, that didn't really matter.
No, of course not.
Because it only had, as long as it worked for 3 or 4 hours, then it was fine. Or not even like an hour or so. There are some people who have come up with various other designs. There's a guy in New Zealand who's come up with a kind of pulse jet which doesn't actually involve a valve at all. There's some crazy sort of resonance system with all sorts of vibrations in tubes. To be honest, I don't understand. And he's powered a motorbike with it once, but I think he had to wear some really hardcore ear defenders.
Thank you, Tony. Lovely to hear from you.
Bye-bye, folks.
Bye-bye.
Bye.
Now, one about sugar here, actually, Dave, which is quite interesting. It's John in Peterborough who says, when you boil sugar, as the temperature goes up, the sugar enters various states, such as soft boil and hard boil. Why does this happen, and why are there so many different states?
Okay, so you've got a very strong sugar solution, sort of syrup, and you're heating it up, and as you heat it up, it starts to boil. And the temperature it would boil at is slightly increased from normal, because if you dissolve a load of stuff in water, it boils at a higher temperature, which is actually one of the reasons why you put salt, you often put salt in vegetables, because that increases the boiling point, which increases the temperature, which it boils at. And so it's a bit hotter, and so it will cook quicker. So it'll get quite hot, and then slowly as it boils, you lose more and more water, so it gets hotter and hotter and hotter. And then what starts to happen is the little sugar molecules have enough energy and a shortage of water, and they start reacting with one another. And they sort of lose one water molecule, or lose a little bit of water from their own structure, and they stick together and form little chains. And I think what the different forms of boil is basically turns into how hard a form of caramel or toffee you end up making, and that's to do with how long these chains are. So if you've got little short chains, then it's still very runny because the chains can move past each other. And as they get longer, then they start to tangle up with one another, and they also start to get darker because they absorb light better. And so as the chains get longer, they get stiffer, and they also get darker. And so you have one end, you've got sort of very light caramel, and the other end a really dark, hard, almost shattering sort of toffee.
Let's go to the phones again now, because Sean is on the line. Hello, Sean.
Hello.
Hello, there you're through to Dr. Dave. What's your question?
Hi, Dave.
Hello.
I just wondered, when an aeroplane hits the sound barrier, you hear this noise, a crack or
a sonic boom.
Sound barrier. Yeah, sonic boom. What, if anything, would you hear if the plane was able to reach the speed of light?
Okay, yeah, the sonic boom is basically a sort of bow wave. It's not just one crack as it goes through the speed of sound. It's actually, it's very like a bow wave. You get this line of very highly compressed air in front of the plane, and another one at a kind of very low pressure area at the back of the plane. And so with some very big plane like Concorde, you used to hear 2 bangs, one from the front and one from the back. And as the plane flies past you, then this basically bow wave goes past, and it wobbles your ears, and you hear it as a crack or as a boom, depending on how far away you are. You can't go faster than the speed of light in a vacuum, but particles can go faster than the speed of light in a material, because light can go significantly slower in a lump of glass or a lump of water. And what you actually get behind them then is you get a bow wave. It's not of sound this time, but of light. and you get this, it's not some Russian, it's something like Cherenkov radiation. And so you get these bow waves of blue Cherenkov radiation as these particles go through. You wouldn't hear anything because, well, if something large enough for you to see, if a plane actually went through a lump of glass close enough to the speed of light, then you'd basically get a huge explosion because there'd be so much energy involved. But with small particles, you just get this rather beautiful blue light coming off.
Oh, okay.
Has that solved it for you, Sean?
Yeah.
All right.
It's a point of interest. Yeah. Thank you.
Thank you very much. Take care. Dr. Dave is here answering your questions, and he has one from that's come from Twitter, I think, Dave. Is that right?
That's right, yeah.
Yeah, OK. It's from Andy Wilkin, and he asks, I have the music on, if all the bottles of Coke in the world were opened, how much carbon dioxide would be released?
This is a very, very rough calculation. I've been attempting to make as many guesses as I can. I've managed to find a figure that worldwide, on average, people drink probably about 2 litres of Coke per person every year. That's about 10 billion litres of Coke, so about 10 million tonnes of Coke is made in the world every year. That's probably, I think this is just Coca-Cola.
Cola in general. Other colas are available.
Other colas are available, but they're not in the numbers I've managed to find. So this number is probably It's probably at least twice this.
Yep.
So there's 5 billion people, so that means there's about 10 billion litres of Coke of this type being made every year. Probably saying about a tenth of that is probably actually around at any one time. That's probably it's probably actually the life cycle of a bottle of fizzy drink is a lot shorter than that, but say roughly. So that means you've got about a billion litres of Coke floating around at any one time. I think each litre has probably about 5 grams in it. So that means you've got about 5 billion grams of carbon dioxide in bottles of Coke around the place, which is about 5,000 tonnes if you open them all at once.
Yeah.
Probably you could double that or quadruple it very easily because there's various other drinks, and if you talk about all other fizzy drinks...
So what effect would that have then?
Not very much.
Not very much?
No.
Just a lot of...
Make quite a good sound.
Make quite a good sound. Now, John in Tiptree, Dave, has said, with all the technology that we've got, have scientists been able to pinpoint the direction of the centre of the universe?
The strange thing about the universe, as far as we know at the moment, is that if you look in pretty much every direction, it looks approximately the same. So there's 2 interpretations of that. One is that we are at the centre of the universe. And we're looking out. And we're looking out from the middle. Yeah. Because if you were at the edge, you look in one direction, and you'd see lots of galaxies, and you look in another one, and you don't see any. In the same way as we're near the edge of of the Milky Way, our galaxy, and if you look in one direction, in fact, it tends to be from south. Then you see a huge number of stars from the centre of the galaxy, which is why the Milky Way is much more impressive from the southern hemisphere. And if you look in the other direction, essentially north, then there's much fewer stars because we're looking out into the rest of the universe. But if you look at beyond our galaxy, then if you look in all directions, it looks about the same. So either we're at the centre, which sounds unlikely, or there isn't really a centre. So there's lots of theories which basically involve the universe either being infinite and it's expanding and just taking up more space. Everything's just getting further apart from one another. Or that it can be curved round in on itself. So it could be if our universe has got 3 dimensions, but you could think of it as if it was 2-dimensional, like the surface of a balloon, and the balloon's been blown up, so everything gets further apart. And so if you drew lots of galaxies on a balloon and you blew up the balloon, they'd all get further apart. But wherever you stood and you looked out at the other galaxies, they'd all look about the same. So I think generally people think that there isn't really a centre as far as we know.
All right, well, Fearless Frank from Felixstowe. Question for Dave. When growing up, he used to go to the local fish and chip shop and get fish and chips wrapped in newspaper. In today's modern materials, if food was placed in newspaper or magazine, would that print now be considered poisonous?
Certainly the reason why you don't get it in newsprint anymore was a hygiene thing.
Yeah.
I don't know whether it was particularly that the newsprint was poisonous. To be honest, I don't exactly know what's in the newsprint. Certainly colour, you could have some heavy metals in there which you wouldn't really want to be eating. But the other big thing is that if it's second-hand newsprint, then people have had their fingers all over it. You've got no idea what the people were doing with it. So it's very hard to be sure that...
Germs everywhere.
Both germs and if someone's been using some weed killer or something and they come in and read the newspaper, you don't know what's on it. So it's quite dodgy. So I think there was a rule being put in not so very long. I can remember it coming in, so it can't be that long ago. That you're not allowed. It's probably about 20 years ago that you're not allowed to use actual newsprint right next to the fish and chips.
Dave has sent an email in because we're running fast out of time. He says the BP oil escape beneath the sea is at a tremendous pressure. How can oil that supposedly was plant life and fish become trapped so far below oceans at tremendous pressure? And how can plant life and anything in the sea not just rot and dissolve? Otherwise, the seabed would be forming oil now.
The simple answer is the seabed is forming oil now. The way you form oil is you get a load of plants and things. It normally happens in plants, animals, just organic stuff. If they sink down to the bottom of an ocean and then get buried relatively quickly, then they run out of oxygen. So at which point, if there's no oxygen there, they can't really rot. They then get buried deeper and deeper and deeper. They slowly decompose a bit, especially they get very deep, they get hot. When they get hot, all the organic molecules in them start to break up. Some of the water is driven off, and what you're left with is sort of black goo of carbon and hydrogen. That tends to then, everything, especially under the sea, all the rocks are completely saturated with water. So this oil which you've now got is less dense than the water which the rocks are saturated with, so it tends to float upwards. A lot of oil just gently escapes over millions of years through little holes in the seafloor, and so we can't collect it. But some of it gets trapped by waterproof impermeable layers, builds up, and then you get a great big sort of reservoir of oil, which is basically, it's not what you think a big cavern. It's basically a load of sand full of oil with water underneath it, pushing it upwards, and so it's trying to float. The big problem they've had with the BP oil thing is it's so deep that it's sort of another 5 miles down below the seabed, that there's 5 miles of water making this oil float upwards, and that's a huge pressure difference. And so it's coming out incredibly fast, and it's just very difficult to deal with.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.